Okay, this is 4.4 example 3 where we solve just another trigonometric quadratic equation. Really important again to look at the restrictions right away. We're going to have to do A and B a little bit differently. A, that angle, which is x, has to be less than 2 pi but greater than or equal to 0. I often call that the kind of single positive rotation restriction. Really important to remember that because of that restriction, our angle is going to be in radians. Now, to solve this, what we need to do is take our expression sine squared x minus 1 is equal to 0 and factor it. I'm going to rewrite that as sine x squared minus 1 is equal to 0, and then we're going to use our difference of squares technique. I'm going to kind of tuck that in the top corner here, that if we have a squared minus b squared, we can factor this into a plus b times a minus b. And in the context of this problem, a squared is sine x squared, so a is the sine of angle x. I'm going to put that in both brackets. Again, in this context, the b squared is 1, so we are going to add 1 and subtract 1 in both of those brackets, or in either of those brackets. From there, because we have a factor times a factor, we can use that to identify that my solution is when sine x plus 1 is equal to 0, which is to say that sine x is equal to negative 1, and sine x minus 1 is equal to 0, which is that sine x is equal to positive 1. Now, these are the kind of, often I call these the tricky ones. They're the quadrantal angles. Students like, usually I think, when they find those exact value fractions from the unit circle, because they can recognize it as a nice unit circle, find the reference angle and go from there. When it is 0, positive 1, or negative 1, we really, I think, benefit from thinking of the unit circle, keeping in mind that the sine of an angle is the y coordinate on the unit circle. That only happens up here at the point at pi over 2, which is 0, 1. So I know that sine x is equal to 1 when x is pi over 2. My other answer is down here, and that point is at 3 pi over 2. That's equal to 0, negative 1. So sine x is equal to negative 1 when x is 3 pi over 2. Now, for both of those angles, if I add 2 pi or subtract 2 pi, I will be out of my restriction. So that's it. That's the only solution. And don't get me wrong, I don't want to minimize what this is, because trig is tricky, but it is very, very similar to the quadratic solutions you've done in the past. Now, B becomes a little bit tricky. I'm just going to write in for myself more than anything that B is about the general solutions. And this is the concept that x is no longer restricted. Now, x can be any real number. And that makes the question trickier, because we talked a little bit about how trig functions repeat. They're periodic, which means that there's infinite solutions to this. And I do not want to write infinite numbers because I have other things to do in my life. So what we're going to do is represent these solutions above, x is 3 pi over 2 and x is pi over 2, as ultimately an arithmetic sequence. And the way that we do that is we take the smallest positive answer and we add 2 pi n, where n can be any integer. And we have to do that to both. So 3 pi over 2 plus 2 pi n, where again, n can be any integer. Now that is sufficient. That describes every single possible, answer for x. But in some situations, in many situations, we can write these two sequences as a simpler single sequence. And I think the best way of doing that is to start writing the answers out and seeing if there's a simpler pattern that appears. So if I put down my two smallest answers, which is pi over 2 and 3 pi over 2, keep in mind that I can add 2 pi n as many times as I want. One of the things that makes that a little bit easier is that 2 pi can be written as 4 pi over 2. Which means my pi over 2 angle, I should say, I'm going to add 4 pi over 2 to that. I get 5 pi over 2. I'm going to leave a blank here. If I added 4 pi over 2 again, I would get 9 pi over 2, and I'll just do one more. I would have 13 pi over 2. And then that pattern would continue. And important to recognize that it continues in both directions, right? In the positive rotation direction, and I'll put that over here. This is positive rotation, and then in the other direction would be negative rotation. All right, the other angle that we're going to deal with is the 3 pi over 2. Now, it's the same thing that we're adding. We're adding 2 pi n, which again can be written as 4 pi over 2. So we would also have 7 pi over 2 and 11 pi over 2 in that sequence. And I think usually this is enough for students to recognize that there's another pattern happening here. We can identify that my first term is pi over 2, and I can add, so to go from pi over 2 to 3 pi over 2, I have added 2 pi over 2. Now, 2 pi over 2 is needlessly complex, so I'm going to write that just a little bit simpler as pi over 2 plus pi. But what's really important is I can add pi once, or twice, or 3 times, or 4 times, or I could subtract pi in the other direction. Now, the way that we can represent that as a single sequence is by multiplying that common difference pi by n, and then indicating that n can be any integer. And I hope we would all agree that writing this as a single sequence is ultimately easier than writing it as several. Okay, that's the 4.4 example 3. Please make sure you're chipping away at this homework. Trig takes a lot of practice. You need to be really comfortable factoring quadratics and comfortable with that unit circle. Please feel free to email me with any concerns, questions, or if you're just maybe missing some materials that you think I might have digitally, I will share that with you.